So what we need to do now is we need to put to practice what we have learned concerning the resistive forces met by objects that are moving through resistive media. Okay, so last time we looked at such forces. In fact, we looked at, this is a small recap, we looked at the drag force experienced by an object as it moves through a resistive medium, and we came up with some expressions for the magnitudes of these drag forces. So the results shown here hold for objects moving with the speed v inside a resistive medium, and as I mentioned earlier, we're considering one-dimensional motions, and as a simplification, we're assuming that the body that undergoes the motion is symmetric, rotationally symmetric. In other words, the body is formed from a volume of revolution, and the motion takes place along the axis of its in the direction pointed with respect to its axis of revolution. Okay, so this is more or less what we came up with. We have the linear law of resistance when we have the low Reynolds number, and this basically says that this drag force D, the magnitude of this drag force is equal to some constant multiplied by the speed or velocity of our object. Now, one thing we need to take into account here is units of B. So we know that the units from dimensional analysis, the units of D are those corresponding to the units of a force. So we can write this in the following way. We also know that the units of the velocity is quite easily written down like this. So this would imply that in this case, that the units of B, in order to make this equation dimensionally consistent, should be m, m t minus 1. Okay, so if you multiply V and B together, what you'll see comes out is the units for the force D. Okay, so we can also apply a similar trick when we look at the quadratic law of resistance. Now, this law comes about when you have a high Reynolds number that describes the flow. And what we have is the magnitude of the drag force, this is drag force again, is equal to now some constant B, which is a different constant from before, multiplied by the square. That's why it's called the quadratic law, multiplied by the square of the velocity. So again, we can do the same dimensional analysis with this equation. Okay, so if V has the dimensions L times t to the minus 1, then the dimensions of this squared is just this. So this means that, well, in order to recapture this here, we should multiply V squared by some constant, which has the units. I'll just write this down now as the units L minus 1 times M. Okay, and this, if you're wondering how I worked out, just take a look back at the notes that we did in dimensional analysis. Now here I did this quite quickly. I was able to do this quite quickly and off the top of my head, but really you can do the same if you just get proficient with the methods we learned there. So I'm just rewriting this again. So you can see that the constant in the quadratic law of resistance is different. Now, in both cases, you have no choice but to find B experimentally. And usually, in questions, B is given. B is either given or assumed to be known. Okay. The other thing is B is positive, as D here, I know I used in my last lecture this notation, D underscore, or with the tilde underneath to represent a vector, but the magnitude of the drag force I'm using is D here. So D here is the magnitude of the drag, and it will be up to us to decide the direction or the sign with which we need to supply this magnitude with in order to construct a force vector representing the action of the drag. So, and as it's the magnitude, D has to be positive. Okay, here in this here, we're assuming that V is taken as positive. Okay. In the first one, V is positive, the velocity. You can think of an object moving in one direction, and this drag force vector opposes the motion, but the magnitude of the drag force will be equal to this, in the linear law of resistance, equal to B times V. Okay, so next what we'll do is we'll employ this in an example. So I have, in fact, let's take this to a new page. Let's start the example fresh from there. Okay, so we're told a spherical stone is thrown vertically upwards with speed u and experiences a linear drag force due to air resistance. So, what is the velocity of the stone as a function of t? And what is the terminal speed it reaches? Finally, we're asked to find the maximum height reached by, and this should be stone. Okay, so answer. So what we should do first is draw a diagram to represent this scenario. So we have a stone moving vertically upwards. So this is the motion. And at some point, let's say at the point O, it was projected upwards. So this is Y. Okay, it was projected upwards. This is our stone. This O was the initial position. And this is our reference frame. So now, okay, all that's in place. We need to decide in fact, you know what, let me just move this a second. We need to decide the forces that act on the stone. Well, clearly, stone moves upwards, so we know that it's acted on by our good old friend, which has magnitude mg, so this is the gravity force, and this force acts downwards. Okay, and this will represent by Fg. And also, it experiences, what we're told is this stone experiences Sorry, let me just get something that's a bit clearer. Experiences a linear drag force due to the air resistance. So we have a vector, another vector, now I'll add this in, which acts downwards, which opposes the motion. Remember that the motion is vertically upwards, so this is our drag force, Fd, this vector. And the magnitude of this is, let me just rearrange this. The magnitude of this is B times V. So this motion takes place with velocity V. And here for the stone moving upwards, the velocity is positive, which is consistent with the positive direction. It's consistent with the positive direction of our y-axis. Okay, so what are these forces, Fg? Well, Fg is as the magnitude mg, and I use the vector j, but it acts downwards, so we need to supply this with a minus sign, as we've done so in similar examples in the past, where this sign is chosen because force acts in opposing direction to positive y. Okay, positive y direction. In a similar way, so this was our gravity force. In a similar way, we have the drag force, Fd. So this has magnitude d, j, and we must also supply this with a minus sign because it acts in the opposing direction to the y, a positive y direction. So this, remember, drag is the linear force. In this case, is using the linear law. So what we have is minus b, some constant, times v. Okay. And let v, our vector v, be v times j. This is a function of time. Okay, so this is a function of time. So what we do is, well, we've wrote down all the forces. We simply need to now use Newton's equation of motion and balance everything up. So this requires us to put things into this formula where F now should be the resultant force acting on the object. Acting on stone. Okay, great. So, well, what is it? Well, F is some, if it's the resultant force, it's the sum of forces. So what we have is minus, actually I jumped a step. We have to add FG to FD. And we'll calculate this on the next page. So this is where we're up to. Okay, this is where we're up to. And what we'll do is we'll now start to substitute everything in that we know, and then write down the final equation. So now here then F, capital F, our resultant force is going to be minus mgj plus, and then I have minus bv of t, v as a function of time, times j. And then when you put all this together, what you have is this, minus mg plus bv all multiplied by j. Okay, so this now goes into the equation, call it star, in star. What you'll have is m. Now I'm going to use the representation of the vector v. v dv by dt j equals minus mg plus bv j. Now, these two are vectors on the left and the right are only equal if the components are equal. So this means that that we get this. And this is our differential equation for v. So this is a differential equation for v, and you have plenty of experience at solving these. Of course, you can see it's separable. You can also see that if you're proficient with integrating factors, you can dive right in and solve this. So, solving. So this we'll call dagger. So now we'll partition this part up. So this is solving dagger. Now, we were asked to find velocity as a function of time. So this is what we're going to do now. So dagger can be written as, now I'm just going to divide through by m, and I'm also going to make some manipulation on the right hand side. So if I keep dv by dt on the left, I have this, and then I need to multiply it by something corresponding to what was on the right hand side. So I would like to take a factor of b out from this so that I have, excuse me, there is a typo, I need brackets there. Okay, so that I have b, I'll take b out so that what I get is this, v plus mg over b. Okay, that is what I have. Now, I'm going to use the method for solving separable equations. So next, I'll rearrange so that I have my function of v all on the left, and then I'll integrate with respect to t. So divide by this factor, and then we get this. 1 over v plus mg over b dv by dt equals minus b over m. And next, what we'll do is we'll integrate with respect to t. Okay. We'll integrate now with respect to t. So that we get the following. We get this. Now I skip a step here because this is straightforward. I put the arbitrary constant of integration there. Oh, this is, remember, just constant here. So I can integrate this no problem on the right hand side, arbitrary constant. And we'll get this with the initial conditions. later. And simultaneously, on the left, well, this is just integral of v plus mg over b with respect to dv, which of course standard integral gives you this. Therefore, ln modulus of mg over b equals minus bmt plus c. Now I'll rearrange. I'll take the exponent of both sides. And what I'll eventually get, as we've done so many times, what I'll eventually get is I will get this, which is, this is, okay, let me do it step by step as I've done so in class. Okay, so I have this. Let's see. E minus b over mt plus c, which I can partition out. Okay, so this tells me that I have a e minus bm over t, if I'm not wrong with the signs. So what about this? Well, this a, it's basically connected with our arbitrary constants. It's just plus or minus c. Okay. So now, with this in hand, I need to find a. So recall, initially, that I have v is equal to u, I dot e, v of 0 equals u. That was the premise of the question, if you remember. It's projected upwards with a speed u. Okay, so that's our initial condition. And let's use this. So I have v of 0, of course, equals u. But then, due to our formula here, I have the following. I have clearly a times e with the exponent 0 because I've subbed t equals 0 in. I have this minus this. Okay, so we can rearrange this to find that a is u plus mg over b. So now our velocity as a function of time stands as this: u plus mg over b multiplied by e b m t, b over m, sorry, multiplied by t minus bg, pg, mg, got the bg's on the brain, mg divided by b. Now, all right, so that's our solution. Good, so this is the first part, partially done. So with this is answer to first part of 1. The second part was what is the terminal, or what is the velocity? In fact, let me read this. What is the terminal speed it reaches? Okay, so terminal speed, so this is looking for the speed achieved in the long time regime. Okay, so this is our solution. Final part, what is the speed achieved in the large time regime, i.e. what is the terminal speed. Okay, good. So, well, simply look at the limit. Which is easy to do. So we first of all we know B and M are positive. Hence, this term decays exponentially. In time, or as t goes to infinity. So eventually what we find is the limit of this is just minus mg over b. Okay. So that's what it is. So basically your graph of the solution looks something like this. Time, there is minus. And this corresponds to when it's falling back down. Okay, so you have minus, you have mg over minus mg over b. And you started with some speed u, this is our velocity v, and then your graph does something like this. Okay, that's what it does, which is quite understandable because, well, you throw this up, object moves upwards, our positive direction for y. It's also pointing upwards. So in this region, object moves up. Now, when it reaches the maximum height, it instantaneously has a vertical velocity equal to 0. So here, this special point where it crosses the axis is at max height, and we're going to grab this in a second. And then in this, it starts falling down. Back down. And that's the interpretation of the results. Okay, good. Now, what about the next part? Well, the next part asks us to find the maximum height reached by the stone. Okay, so here we go. Find maximum height reached by stone. So I'm going to use a different trick now. So let me just explain something. We could use our formula for V. So we could, and this is similar to the Romeo and Juliet cream egg example that we did some time ago. We could use formula for V and integrate with respect to t. Use initial condition. And then these are all the steps. Find vertical displacement. As function of t. Find time of max height, Remember, this is when v equals 0, as I demonstrated on the graph before, when v equals 0, and then sub in displacement. Okay, so quite a few steps to do. So that's 1, 2, displacement at 3. Okay, find the max height, 4, and then 5, sub in displacement. So, this is quite involved, but there is a quicker way. Remember what we did with Romeo and Juliet was to use the related rates. So let me show you the quicker way. So recall. Now let's go back and grab this. Recall that you have this equation. Now, on the left-hand side, I have the velocity. Okay, so what I can do is I can do the following. Using the chain rule, I can do dv by d. This is dv by dx multiplied by dx by dt, which is exactly what we did in the Romeo and Juliet problem with the cream egg. So this is v dv by dx. Good. So now I've converted the problem into a problem of finding v as a function of x, which will hopefully cut out all this business of having to do these 5 steps. Okay, so what do we need to do? Well, again, it's in the separable form. We can take it, we can handle it. So rearrange. It's in separable form. So that we get everything with v on the left next to the derivative of v with respect to x, and then whatever else is on the right. So we have v plus mg over b dv by dx equals minus v over m. Okay, so that's what it is. Next. So, well, the two things I can integrate. With respect to x to find the max velocity. Max velocity to find v as a function of fx, but it's overkill. So, why is it overkill? Well, we just need a value for max height. We simply need x. By the way, I used x. That's terrible. Can I just adjust this? It should be y. Why? Because y is our coordinate that points upwards, is our variable for upwards displacement. So I just replace an x by y. Okay. So we simply need to find max height. So what can we do? Well, let's just paste this there. First of all, so we have this equation. First of all, let's review the conditions we have. So we know when y equals 0, the speed v, vertical velocity is u. That's our initial condition. So the point from where it's projected, it has an initial speed u. we know initially. Now, that this happens when y is 0, v equals u. Additionally, when we reach max height gives us the following condition. There's a magical value for max height, capital H, where v is instantaneously 0. Okay, so why not take this equation, take EQ, and integrate with respect to x. He's obsessed with x with respect to y within these limits. Within limits corresponding to the above information. Okay, and this we can do. So, okay, what happens is I'll integrate both sides with respect to y. Okay, dy. This is just a constant, so I basically have this. I can take the constant outside. This on the left hand. Now, I did promise some limits. So the height extends from 0 to capital H, 0 to capital H. Now, I'm going to use chain rule and make a change of variable. Okay, this gives us dv, an integral with respect to dv. So switch limits now to those in terms of v. We have integral, almost there, integral. Now, I'll just put this down, mg over b dv equals b over m. Now, this is a straightforward definite integral on the right. To compute it just gives us h. But I have to do something about here and here. Well, I know that when I have the limit 0 height, that my initial speed was u. Very good. And I know that when I'm at max height, my initial speed, my speed or velocity is instantaneously 0. So 0 and u are my upper and lower limits, respectively. Okay, so great. What about this integral? Well, this is easily computed because what I'll do now is I'll just add and subtract this in the numerator. And as you can see, what this gives me is the following. This gives me 1 minus mg over b, some constant, over v minus mg over b. Okay, so we're just going to integrate this and then we're going to plug in the limits. Okay, plug in the limits very well. So now we just need to do this integral. So I'm going to take this, and what we'll do is we'll insert this result. So this implies that we have the following. If I haven't made a mistake, I'm going to take this. Yep. I'm going to integrate this with respect to v between these limits. Okay. right, so easy for the first part. Well, actually easy for all of this, I think. So this is just integral of 1 dv minus mg over b integral u over v minus mg with respect to v. Then what we have is the thing that we calculated earlier, that this is equal to. So this one is minus u. Okay. This one here, of course, gives me the following to compute. Logarithm. Sorry, there is something wrong here. That should be plus. That should be plus. And that should be plus. Okay. So this is logarithm v mg over b modulus. We'll plug in the limits and see what we get now. Equals minus b over mh. So this then means, so we have minus u minus mg over b. In the brackets here, I'm going to plug in the limits. So I have log of the modulus. If I sub in v equals 0, I have log, let me just write that, v equals u and v equals 0. So the first limit, I have log of the modulus of mg over b. And mg and b are positive constants, so I don't need to worry about the modulus. I just have this for the first limit. And then I'm subtracting the lower limit, which is again positive because it's the speed u is positive. So I have L u plus mg over b. Okay. Therefore, max height h is simply this formula rearranged. H equals m. I'm now dividing by minus b over m, so I have m u over b. Okay, so now this becomes plus m square g over b square logarithm of this. And well, that should be it, really. So let me just double check. This seems to be okay. Yeah. Okay. So yeah, after all of this, you didn't need to construct a formula for v as a function of h. You just simply, a function of y. You just simply had to use the limits. Okay. So that's it really for this example. When we come back next time, we'll be looking at a slightly different scenario involving the linear law. And then we'll try and look at something with the quadratic law of resistance. See you soon.